Hello everyone, welcome to CR Last Minute Revision app. So the topic for today is network security for BCA 4th semester students. I am Mr. Srikanth, Assistant Professor in Department of Computer Science and Professional Trainer in the Department of Computer Science. We are here for understanding network security in our SIA Last Minute Revision app. Let us go with the paper pattern. As we know, you'll have two sections here, where in the part A, you have 10 questions and you need to answer all the 10. Each question carries 2 marks, so it is going to be total to 20 marks. Then you'll have section A, part A, 10 questions will be given and you need to answer all the 10, which gives you 20 marks. Part B will be your Part B consists of 5 questions and you need to answer all the 5. Each question carries 10 marks. As we know, we have 5 units in our syllabus. From each unit, you will have a question with internal choice. And again, see, kindly remember, you have question 2 with the 2 internal questions, question 3 with the 2 internal questions, and you need to answer complete question 2 or complete question 3. If you try to answer A from question 2, B from question 3, you are not going to get full marks. Done. And one another important thing is, all the questions comes with the internal choice. Technically speaking, any question what we are going to discuss today is only for 5 marks. Done. Though the question is for 10 marks, but you have internal choice for each and every question. So technically speaking, any question what you are going to answer, any question what we are going to discuss today is of 5 marks only. Okay, remember that, and you have to manage your time same way. Done. All the best from the management of SIA for your end semester examinations. We will go with unit number 1, and when I move forward to unit number 2, unit number 3, 4, 5, the ultimate story of this particular subject is I am a sender sending a message to my receiver. In between this, there may be a chance of someone reading my message, there may be a chance of someone corrupting my message, sending a different message to my user. How are you going to eradicate it? How are you going to protect your data? That is the entire story of your all 5 units. The very first unit discuss about the symmetric keys, and in the upcoming units we discuss about the algorithms for the protection of our data. That is going to be the ultimate story of this unit, all 5 units. Without making much late, we will start with our unit number 1. Done here, we will be discussing about explain symmetric cryptography in detail. This question is being asked in June-July 2024 under question QA. Again, which carries for how many marks there? 5 marks. One simple thing which you need to notice, these are the questions which are identified by our team, and we imagine, like we assume these questions are going to be appear for this upcoming end semester examinations also. The 4th and 6th semester examinations of BBA, BCom, BCA has almost satisfied all the last minute revision questions of our SIA, and trust us, 80% of the questions what we discussed here are in the question paper. So that credit goes to our team who worked and who were able to analyze the question paper. So these are going to be the only the important questions we predict in the upcoming semester question paper. We will be not discussing the entire syllabus. Make sure that. So the very first question is explain about symmetric cryptography in detail. So what is cryptography first? We are going to send a message to a receiver, and when we are sending a message, we encrypt the message and we send the message in unreadable format. So user receives it, then user will decrypt it. The unreadable message which transported from my place to receiver will again transport it into normal language. Then the message will be passed safely. That concept is called as symmetric cryptography. Symmetric cryptography is a method of securing data where the same key is used for both encryption and decryption. Sender uses encryption, receiver uses decryption, and you can see it in this particular diagram. Original text will be encrypted to the ciphertext. For this, we use the symmetric key. The same symmetric key is also available with the receiver. When the receiver receives the ciphertext, that will be converted into original text. This concept is called as symmetric cryptography. And how are you going to achieve this in the day-to-day communication? Done? We will discuss about this. And to make it a little more clear, the main principle behind the symmetric cryptography is it converts the readable format into unreadable ciphertext, and then it is shared with the user in a public network or in a unsecured network. Then receiver receives this ciphertext, and receiver will again use the same key. Receiver will decrypt this unreadable format into readable format. That is the main principle of symmetric cryptography. And these are the some simple notations which supposed to be used to get good score. Done. So for the encryption, we use ek of m, where m is my original message, and when you apply the encryption with the symmetric key k, you are going to get the ciphertext. Now this text will be transported to the receiver. Receiver will do what? Receiver will perform decryption. And dk of c, the ciphertext, unreadable text, what received, when we apply the same key k, you will decrypt the ciphertext unreadable format into original message. This is how the communication can be established between unsecured user and sender and receiver on the unsecured networks. And this is your identity. Decryption of encryption of original message will give you the original message again. Here M is the plain text, C is the ciphertext, and K is the secret symmetric key which is shared between two users, sender and receiver. Working procedure. The sender can and receiver can make a agreement, can agree upon a common symmetric key. Right? The sender and the receiver agree upon a common symmetric encryption algorithm, and they can securely exchange the symmetric key, the secret key. Again, you may have a doubt, if someone gets the secret key other than the sender and receiver, if someone gets the secret key, they can read the message. Yes, this is the disadvantage of symmetric cryptography. Then when someone, the third party, receives the secret key, that fellow will be able to read the decrypted message. That's one of the biggest disadvantage of symmetric cryptography. Okay. So the sender encrypts the original message, that is the plain text, into the ciphertext. Now this text will be sent over the unsecured network. The receiver will decrypt the ciphertext using the same key to translate the unreadable format into original plain text. Right? This is the working principle. How does it works? Sender, receiver first will make an agreement on the common key. The key will be shared with both of them. Sender will send a plain text. This plain text will be translated into unreadable format. We call it as ciphertext. That will be transported over the unsecured network to the receiver. At the receiver end, receiver uses the same key and receiver will decrypt the data. So the unreadable format is again converted into readable format. This is the working procedure. And why the symmetric cryptography is more famous and why many people are using it? Because it is quite fast and efficient. It is very simple to implement. Because it is quite fast and efficient, it is simple to implement. It is good for real-time applications. And coming to the drawbacks or the disadvantages, key distribution is a problem. Sender and receiver should agree on the same key, and if someone gets the key, your message is unsafe now. Scalability issues and as well as compromise risk. That is what I said, compromise risk. And the same thing I will be able to explain you in a very easiest and simplest way with this simple diagram. Okay, I am trying to give you the basic idea behind the symmetric cryptography. What is the basic idea? The same common secret key is used for both encryption and decryption. The same common key is used for both encryption and decryption. Suppose there are two users, Alice and Bob. Alice will send a message in the form of a plain text, that is your original message, hello Bob. Now this message will be sent over the network, and when this started, the encryption will take place and it will convert the original plain text into unreadable format, the cipher text, using the secret key. Now this will be transported over the network, that is insecure channel. Then your original message can be stored something like this. Now this message will be received by the Bob. Bob, before reading it, he will use the decryption technique with the same secret key, and the cipher text will be converted into plain text. The same message, what hello Bob, is received to the Bob, but in the unreadable format over the insecure channel. This is symmetric cryptography. How does this work? What is the working procedure of it? Two users, Alice and Bob, will agree on the same secret key K. Alice uses this key and Alice will encrypt the plain message into cipher text. The encrypted message is sent over the network. Bob will receive the encrypted message by using the same symmetric key K. Bob will decrypt the message. The unreadable format will be converted into readable format. Same key plus encryption is equals to ciphertext. Same key plus decryption is equals to original message. Done here. This is your first question of unit number 1. What is symmetric cryptography? We will jump into the question number 2. What are the potential vulnerabilities of public key cryptography, which is asked in May 2025, question number 2B for 5 marks. See, when I use the word vulnerabilities, it is the damage or the attack what your data is going to face. Then what are the attacks? What are the chances of exploiting your data? That is your vulnerabilities. Okay. Now we will discuss about the vulnerabilities of public key cryptography. There are different kinds of chances where your data can be attacked. The first chance is man in the middle, MITM attacks, right? So when you send a message to the receiver, there may be a person in between you and your receiver, and that fellow might change the entire data and can be sent to the receiver. This is a man in middle attack. An attacker secretly intercepts the communication between two users. The attacker replaces the original public key with their own public key. An attacker will send this message to the user. So the sender unknowingly encrypts the messages using the attacker's key. Now before your receiver reading the data, attackers will read, modify and forward the message. So your data is been damaged, your data has been attacked, your data has been compromised. This is your first chance of attack what you have on the public key. What is that? Man in middle. There is a man in between the sender and receiver. This man will replace the original public key with their own public key. When sender sends the message, the attacker will receive the message before this receiver. Attacker will change the data, will read the data, and a false data might be sent to your receiver. Second thing is the private key compromise. So instead of using the public key, we use private key, where two users are agreed on the same key. Now this private key might be compromised. If the attacker gets this private key, the messages what you are discussing can be encrypted, can be exploited. That is the issue of private key compromise. The private key must always remain secret. If not, what happens is, if attacker steals the private key, they can read your entire conversation. They can read the encrypted messages, pretend to be legitimate user instead of you, they might chat with you. They might send messages to you instead of the actual receiver. That is pretend to be legitimate user. The third case is performance over head. Suppose when we are going with this vulnerabilities, then here the one chance is not only the attacker is going to exploit your data, there may be a chance of overhead. Because when I want to use security, when I am using the public key algorithms like RSA, it requires more calculations, because as the encrypted message length is increased, then here there are less chances of identifying it. If the number of bits in your data are weak, there are high chances of cracking it. Done. So the algorithms like RSA require much complex calculations, and they are slower than the symmetric key algorithms. Therefore, they are not suitable for encrypting large amounts of data directly. And if you use them, you are going to face performance overhead. Your performance is going to decline. That's one of the problem what we have with this encryption. The another thing is mathematical dependency risk. Public key cryptography Public key cryptography relies on more mathematical calculations like prime factorization. In the upcoming chapters, we will see how does this prime factorization helps your data. And the latest coming systems like quantum computers or futuristic algorithms can easily solve these problems and can easily break your encryption, can easily exploit your data. Done. Because of the futuristic technology, or this quantum computers can break today's encryption techniques very easily. That is the problem with mathematical dependency risk. Certificate authority dependency. Again, this encryption messages are provided by the certificate authorities like NIS, NBS, and if the certificate authorities are compromised, they may get the fake certificates. They may get fake certificates, and attackers can then impersonate as legitimate users. This is one more disadvantage, right? What is this? Public keys are verified by using the digital certificates issued by the certificate authorities. If the certificate authorities are compromised, attackers might get the fake certificate and they might misuse it. They might behave like the legitimate users, and they might send the messages, they might send the data transportation between user and sender. Lack of forward secrecy. If the encryption has been broken today, what all the previous messages and conversations we made, all of them are unsafe. That is lack of forward secrecy. If a private key is compromised in future, previously encrypted messages may also be decrypted, right? There is no secrecy, there is no privacy for your old data also. That is this lack of forward secrecy. Okay. This is about your public key encryption. This is about your public key encryption. See, we discussed about man in middle. We discussed about mathematical computations. We discussed about fake certificate authorities. Done. All these things might create the vulnerabilities for the public key cryptography. The third question in the unit number 1 is, how does random number generations impact the overall security of cryptographic protocols? Just now in the vulnerabilities we have discussed, mathematical computations are going to create a very important impact on the cryptography protocols, because the number of bits in your data is increased. You have the less chances of attacking. If you have a small amount of bits, the chances of guessing the data is damn high. Done here. So we have to go with random number generations on the overall cryptography protocols. And this particular question is asked in May 2025 under the question number Q3B, which carries 5 marks. So random number generation is very important in the cryptography protocols, because these things will create unpredictable values which is used for encryption. The random Number generation is very important in cryptography protocols because RNGs can create unpredictable values which are used for encryption, which are used for password, session IDs, and digital signatures. That is the reason when you log into some banking or some high level applications, they will ask you to create a password with at least 8 characters, with at least one capital digit, one capital character, one small character, one digit, one symbol, so that the chances of breaking it, so the chances of guessing it are minimized. Done. That is the reason random number generations are going to create a very good impact on your cryptographic protocols, session IDs, passwords, or digital signatures. Because if the random numbers are strong, they are unpredictable. If random numbers are weak, they are predictable and attackers can easily break the security. So generating these random numbers is very important for us. Now, what are the types of random number generators we have? The very first type is TRNG. What is this? This is the true random number generator. This generates the numbers from physical phenomena like thermal noise, like your radioactive decays, and outputs are truly random, unpredictable, and non-repeatable. Right? This true random number generators will generate the numbers from the thermal noise, from the radioactive decays, and this true random numbers are unpredictable. Done, and it is not easy for anyone to break. These are going to create a very strong authentication to your messages. The second of kind is PNRGs, that is pseudo random number generators. Here we generate the random number sequences and outputs appear random, but it can be breakable easily. This is not that tough as your last one. True random number generators. This is pseudo number generators. This appear to be very random, but it can be produced if the internal state is known. If the internal pattern is known to me, it is easy for me to break. Third one is cryptographical secure messages, secure numbers, that is CSPRNGs. These are specialized numbers which are designed for the security. Future outputs remain unpredictable even if you know the part of the pattern now. Even if you know the pattern now, predicting the future patterns is going to be very, very tough. That is cryptographical secure PRNGs. Again, what is PRNG? Pseudo random number generators which are cryptographic. Done. And advantage with this is future outputs remain unpredictable even part of the sequence or the pattern is known now. The fourth of category is this. Now we are done with this random number generators. We have true random number generators, pseudo random number generators, and cryptographical random number generators. Okay. True random number generators are produced by your natural radioactive decays or thermal noise. Pseudo random number generators are random number generators which are not that safe. That's the reason we went with the cryptographical random number generators. Now, what are the properties of good random number generators? The very first property is statistical randomness. Produces values that pass randomness test and shows no bias, right? The properties, the importance or the advantage of using the random number generators is they pass the randomness, they are chosen randomly, and they show no bias. And the second important property is unpredictability. Future numbers cannot be predicted from the past numbers. From the previous outputs, patterns, you will be not able to predict the future. The third one is non-compressibility. Generated sequences contain no detectable patterns, so it is not compromised easily. After this, the another property is long period, and we can guarantee if the numbers, if the number of bits are damn high, the chances of repeating in the nearby future is very less. That is long period. Numbers do not repeat for a very long time, ensuring reliable operations. Okay, so these are the properties. Here, what is the impact on the cryptography security by this random number generators? Encryption keys must be random, and encryption keys must be strong, because weak random numbers create weak keys. The numbers should be big. If not, you are going to get weak keys, and weak keys will create weak messages, weak encryption. Session keys and noise. Noise prevent replay attacks. Random session keys make each communication unique. So, if I use a random key now and if it is known to the attacker, attacker cannot predict the future key. That is this, right? Session keys make each communication very unique. Third one is digital signatures and hashing. Digital signatures done here cannot be easily forged. Prevents attackers from forging the signatures. You cannot do forgery signatures because digital signatures are going to be very secure. We use the encryption technology for transporting the simple digital signatures into the encrypted data. In the unit number 4, 5, we will discuss about this. Symmetric and asymmetric encryption. In the unit number 1, the first question was symmetric key, which was the common key used by the two users and they were sharing it. As we are into the advanced encryption securities, and we also have the RSA algorithms which uses random values during the operation, that creates a biggest impact on the symmetric and asymmetric keys generation. Randomness improves confidentiality and security, done because it is unpredictable. Security risk from the weak random generators. The very big threat is brute force attack. The very big security threat is brute force attack. Suppose I have a pin number like 1, 2, 3, 4. Suppose I have a pin number with 4 digits, 1, 2, 3, 4. Done. And attacker knows that I know 4-digit pin number. Now, what is the chance, what is the probability that attacker cracking my password? The maximum chances 9,999 options only, right? If I keep a pin number with 4 digits, attacker can crack it by trying how many, how many example like 1, 2, 3, 4 is my pin number. He can try with 000, 001, 002, 003, like 111, 112, 1113, 1114. Like this patterns can be tried by the attacker, and the maximum available options is 9,999 only. So there is a high chance like my password, my pin number can be guessed by the attacker. Instead of that, if you go with the 8-digit pin number, now understand how many chances attacker need to try. How many possibilities your password can generate. Done here. Trial, that trial is called as brute force attack. Predictable numbers reduce the number of possible keys. Done here. See 1, 2, 3, 4. It's a predictable thing which has only 4 digits, and how many chances they have? Only 49 chances. So it is easy for them to predict what is my pin number. That is the brute force attack. Predictable numbers reduce the number of possible keys. So we have to go with unpredictable numbers, rather a big number. Attackers can guess keys more easily. Weak numbers gives you weak keys. Attackers can guess it. Strong numbers gives you strong keys. Attackers cannot guess it easily. Brute force is the biggest risk what you have for your encrypted data or your PIN numbers. Session hijacking. Attackers may predict the session tokens, and attackers may behave like the legitimate users, and they join the session and they steal your data. That is session hijacking. And the another important thing is digital signature forgery. Weak numbers will allow the attackers to make signatures forgery done here, and they can be used for different kinds of things. Private key expose. Weak random numbers may help attackers to reconstruct secret keys very easily. So the ultimate story of this is, if you generate strong random numbers, you have strong keys. If you generate weak random numbers, you have weak keys, and weak keys have the highest chance of exploiting. Done here. So we will have a very quick revision. Our question consists of two important things: the impact of random numbers and cryptography, and the second thing is what? Security risk of the weak random numbers. First, how random numbers are impacting your cryptography protocols. Second thing is how weak numbers are creating problems to you. Okay. First is impact on cryptography. We can generate key. Encryption keys must be random because weak random numbers create weak keys and they are predictable, easily they are attacked. Second, session keys and NOS. NOS prevent replay attacks. Random session keys make each communication unique, so that even if the previous session IDs are known, predicting the future session IDs is impossible. Digital signatures, making the forgery signature is going to be very tough when you have random values. Strong random values will make each signature unique. That will prevent the attackers from forging your signatures. Fourth one is encryption algorithms like advanced encryption standards, AES or RSA. It's an algorithm which is a combination of three scientists. Use random values during the operation. Randomness will improve the confidentiality and security. So there is a very serious need for us to generate random numbers. This random numbers will be padded with your message, and this padded message will be sent to the user, will be sent to your receiver, so that user guessing this padded message is a difficult task, because the random numbers added by you are very strong. If you add a weak random number to your message and it is sent to the receiver, attackers can exploit it very easily. Okay. Now, what are the security problems from the weak random generators, weak random number generators? It can be easily predictable. Limited number, high chances of predicting it. Predictable numbers reduce the number of possible keys. Attackers can guess keys more easily, right? Session hijacking. Attackers may predict the session tokens based upon your previous token, based upon your previous ID. The futuristic IDs can be easily attacked. Digital signatures forgery becomes quite easy now when you have a limited number of random numbers. A weak random numbers will allow fake signatures to be created very easily. And the last one is private key exposure. You know, the private key is used to transport the data from the sender to receiver. If private key is compromised, any attacker can sit in the place of receiver and can read the messages before the actual receiver. That is your private key exposure. Done here. This ends the cryptographic protocols with random numbers. Okay. And the next question is, write about cryptographic protection on your databases, which is appeared in the month of June July 2024 under the question Q3B. What is the question? Write about cryptographic protection of databases in detail. Right? As we know, databases are the collection of logically related records, and the entire data of the organization is stored in the database. If the database is compromised, the entire data of your organization is at the threat. Then how you are going to protect it? That is this. Cryptographic protection of the databases is a security technique which protects the sensitive data that is stored in the databases using the concept of cryptography and hashing. What is cryptography? Protection of databases. It is a security technique which protects the data stored in your database using the concepts of hashing and encryption. It ensures that authorized users only can access your data. Authorized users only can read your data, write your data, update your data. Why it is needed? because the entire organization data is stored into your database and you need to give the protection to your information. It might leak the personal details of the employees or it might leak the business secrets of your organization. That is going to be a biggest problem. Prevents unauthorized access, keeps data encrypted even if the data is compromised. This is going to be the most important feature, the game changer of this scenario. Then, even if your database is compromised, even the unauthorized user got the access over your data, they cannot understand your data because it is encrypted. Okay, allows legitimate users to retrieve specific records safely. Even after your database is compromised, the authorized users can download the data very safely. Done. This is the important features why we need to provide the protection to our databases. Confidentiality of information is increased. Unauthorized users cannot access your data even if your database is compromised. The data is unreadable, and even if a database is compromised, the authorized users can download and access the data safely. What is the purpose of cryptography protection? Secure record access. First is secure record access. Only users with the authentication, only users with the authorization can access a record. Unauthorized users cannot access a record. That is secure record access. Prevents mass data theft. No one can easily download or read the data. That is prevent mass data theft. Third one is protects sensitive information. The very sensitive information cannot be placed in the form of a plain text, cannot appear in the form of a plain text, so that you have a better security to your data. Maintains usability. Authorized users can still search and retrieve the data even if the database is compromised. Core method, index and data field separation. To provide cryptography, right, the metadata in your database is stored separately and your actual data is stored separately. That is, the database is divided into two parts. We have our metadata separate and we have our index data separate. Done here, this is metadata. Can I have a break of 2 minutes, please? Uh, Dear students, in the comments section, we see many of them are asking to give direct important questions and answers rather than explaining them. So this PPT, PDF, important questions, answers, and everything is available in your SIA app. You can log in and you can access it. But the simple trial from our side is, if there is any student who did not go to the college or did not understand, or we were not able to confident in answering this, that might help them. This entire PPT, then it is available in your SIA application. Download the SIA app and you will be able to access this PDF, notes, important questions, and everything. And there was one funny comment from one of the users saying that I will remove the important questions from ChatGPT. No, dear, ChatGPT cannot predict the questions of Usmania University. No, our team has done some basic homework and they predicted 80% of these questions appeared in the last examinations. Okay, so please cooperate with us, give us certain time. We will discuss all the questions topic by topic. Done, dear. And all the questions what I'm talking here are very important for you. So you just run through the session, you just wait for the session for the unit 345, and we will have this discussion and as well as important questions. Okay, dear. So as I said, in the databases, you'll be having two important fields. Maybe I will cut short the explanation process. If someone is in a need, I'm sorry to them, because most of the public is demanding to go with the question and answer directly. Then here, I'll try to cut short the explanation process. Okay. So the database protection, we will have two important fields, index field and the data field. Again, Nana, you're asking about important questions. Do you know what is hashing? Right, your original data what we have is not visible to the users. On this original data we will create a hash table that is called as index field. Then this hash table will have the pointers to the actual data. So when the attackers try to attack your data, they get the index file but not the original file. Then that's how we protect our data in the hashing. So we have two fields here, index field, that is one way hash function to hide the original key, and the data field where we have the name, address, roll number, phone number, certain kind of things, that is your original data. Okay. When the user sends the index file, it will go to the original data. If the match is found, the user uses the original key to decrypt the corresponding data field and access the actual information. Okay, so I'm just moving forward here as per your request. Cryptography protection of databases, the simple flow I'm going to show you, the hashing technique. Enter search key, example Sharma, but Sharma is the original key and we are not going to search for the Sharma, we are going to use a hash key. Search key is hashed using the same function hash. Now we will search for the Sharma in the index field, not in the original field. If the match is fine and you can see the index field, they are all encrypted. Not when the original match is found, then I'll go to the encrypted record and I'll use the decrypt and I'll display the message which is related to the Sharma. That is how you save your data. Then you are not searching for the original message, it will be encrypted to the index key. Index key will point to the original data. We will have encryption, we will have decryption. In short, search key converts to hash. Hash will search for the matching index field. If the index field is found, we will get the encrypted record and it will be sent to the user. User will decrypt, user will read the actual data. Okay. What are the advantages of this? Targeted record retrieval, prevents bulk extraction of the data. Any suspicious actions can be easily identified. No plain text storage, entire thing is stored in the form of hash tables, index fields only. Cryptography access control. What are the disadvantages? Limited search flexibility, because if you want to search for the index file, imagine if you have a huge database, how many hash tables I need to maintain. That is going to be the toughest job. So we have a limited search flexibility. And we have a chance of brute force attacks. Again, as I said, the number of possibilities are limited, so the attackers can easily guess your data. High resource consumption. We need to maintain the database separately. We need to maintain the metadata separately. You need to have a database, you need to have a repository, and you need to have a trained professional for it. So obviously what happens? Resources consumption will be damn high. Done. This ends your unit number 1. We will jump into our unit number 2 now. Okay. In the unit number 2, you have a question about subliminal channel. Explain the detail about subliminal channel, which is appeared in your June July 2024 questions under the 4A. The subliminal channel is a hidden communication channel which actually goes with your actual message. Done. Which actually goes with your actual message. It is a hidden communication channel used in the cryptography. What happens is the sender will secretly send a hidden message with the actual data. If any attack happens, the attackers can see the actual data but not the hidden data. The actual data is only trying to cover up your hidden message. By this, your hidden message can be communicated with the receiver. Especially this kind of communication is used in the spy communications. Okay. So what is subliminal channel? It is a hidden communication channel in the cryptography. It allows the senders to secretly send the extra information inside a normal looking digital signature. When the attack is happened, people will encrypt this, decrypt this normal digital signature, but there is a hidden information inside it. How does a subliminal channel work? Let us understand now. First, sender creates a normal message. It may be a simple message which will be transported on the unsecured channel. Second step is secret data is hidden in your actual message. Secret data will be hidden in your actual message by generating the digital signatures. The sender embeds the secret message inside the signature. Okay. What is the first step? Actual data will be prepared by the sender. Second step is now the digital signatures will be embedded with the actual message. That is, the hidden message will be padded with the original message. Third, message is sent. The signed message is sent through normal communication channels. Receiver will receive the message and receiver will extract the hidden information. Right here, this is how your subliminal channel will work. Now, the biggest advantage is outsiders cannot detect it. Anyone who is seeing the data, they will see only the valid digital signatures, but they cannot see the hidden messages existing in your message. Right? This is subliminal channel. What is this? It is a hidden message sent with the actual message. Okay? Example. Suppose a spy wants to send a message. The visible message will be meeting is scheduled for Monday, but the hidden message will be location changed to building B. The actual message, what looks is this, the cover up message. This is the actual message. Now, inside the digital signature, the spy secretly embeds this message. And when the attackers see the message, they only see this cover up message. This hidden message is still safe and your data is still safe. The receiver can extract the hidden message while the others only see the visible message. Right here. So, what are the different applications of subliminal channels? Spy networks enables secret communication in high security and monitored environments. So, you will be able to send the message to your user in the highly monitored environments also. Your message is still hidden. Second, coercion alert mechanisms. Embedded hidden signals in the digital contracts to indicate distress or forced agreements. This embedded hidden signals in digital contracts to indicate that this is distress or forced agreement, not a satisfied agreement. We can send this type of hint to the users. Government digital currency e-tracking. When I'm talking about the e-cash, when I'm talking about the e-currency, then here this embedded traceable information can be included in it so that you can have the genuinity of your e-currency. Corporate document tracking. Monitor and trace the movement and life cycle of digitally signed documents. To whom it is traveled, to unauthorized users it is traveled, you will be able to track it and monitor it with the help of this corporate document tracking. Advantages: hidden communication. You will be able to send secret messages without a separate communication channel. Without a separate communication channel, you will be able to send secret messages. It is going to be one of the biggest advantage. Difficult to detect. Appears to be a normal simple message, but there is an important hidden message under it. Then this is advantage. And we also have couple of disadvantages here, right? One more advantage is it looks non-suspicious because it is just going as a normal message and there is nothing to doubt about it. So it is non-suspicious. High security use enables communication under strict surveillance also. Limitations: this can be misused by the unauthorized users, right? So protocol dependency. Security relies on the underlying signature algorithms. Possible misuse: can be exploited for unauthorized secret communication. Difficult auditing. Hidden messages are hard to identify and as well as verify. Done. So when we have kind of advantages, we also have kind of disadvantages. Okay. So this is your first question in the unit number 2. Done here. We will go with our question number 2. What is zero knowledge proof and how does it ensure privacy in cryptography systems? What is zero knowledge proof and how does it ensure privacy in cryptography systems, which is asked in May 2025 under question number 4b. I want to prove that I know the password without saying to you. I have to prove that I know the password of a certain website without sharing with you, because if I share the password you will be able to know the password, no, you'll get the knowledge of the password, but I want to prove it to you. How? By using the zero knowledge proof we can do this, and there are quite beautiful advantages with this zero knowledge proof. We will jump into the topic. A zero knowledge proof is a cryptographic method which allows one person, we call it as prover, to prove to the another person, we call it as verifier, that I know a secret. Without sharing the secret to the verifier, I have to confirm that I know the secret. That concept is zero knowledge proof. Okay. It is a cryptographic method where one person who call it as prover need to prove the another person who need to call it as verifier that this person prover knows the secret, again without revealing the secret. Without revealing the secret. How do you do this? We will do this. The real world example is, as I explained in the beginning, suppose Alice wants to prove to the Bob that she knows the password to a website without sharing this password with the Bob. That is zero knowledge proof. The traditional method is Alice tells the password to the Bob, Bob verifies it, and it is proven to be true. Now the problem is Bob knows the password, which I don't want to. Then how do you solve it? We can solve it with the help of using zero knowledge proof. Alice performs a special cryptographic procedure. Instead of sharing the password directly, Alice performs a special cryptographic procedure. Bob becomes convinced with this procedure and Bob believes that Alice knows the password. Alice never revealed the actual password, but Alice convinced the Bob that Alice knows the password. That is the usage of knowledge proof. And what is the result? Authentication is successful while still keeping the password secret. Authentication is successful while still keeping the password secret. Okay. So, who are the two parties involved here? Prover and verifier. Prover, the person who knows the secret and wants to prove it without sharing it to the third person. The verifier, the person who checks whether the prover really knows the secret or not. Again, this concept looks something similar, like when you want to log into your application, before giving the password or after giving the password, the application might ask you to send a OTP. The application might ask you to give the date of birth. The application might ask you to answer the secret key which you kept before. Done, Nana. Those concepts are satisfying this techniques only, satisfying this criteria only. Okay. A zero knowledge proof must satisfy three important properties. First one is completeness. If the prover really knows the secret and follows the protocol correctly, the receiver will be convinced for sure. If the prover really knows the secret and can use it correctly, 100% verifier will be convinced, that is completeness. Second one is soundness. If the prover does not know the secret, they cannot successfully fool the verifier. So zero knowledge proof gives you the better security. Zero knowledge. The verifier learns nothing about the secret itself, but verifier is convinced that the first person prover has the secret. That is zero knowledge. Now let us understand how this ensures privacy. The main advantage of the ZKP zero knowledge proof is that private information is never revealed during the verification. And what are the cases, what are the situations, we will try to understand. Authentication without revealing the passwords. Users can prove their identity without exposing the passwords or the private keys. That is the biggest advantage of it. Second one is privacy in blockchain transformations. Cryptocurrencies like Zcash use zero knowledge proof technologies, a real world example. In the entire universe, when we are talking about the blockchain transactions like Zcash, they use this zero knowledge proof techniques. Sender, receiver, transaction amount will be never known to anyone, but still your transaction is successful without knowing the, without revealing the details of sender, receiver and transaction amount, you can make your transaction successful. Secure digital voting. Voters can prove their vote is valid without revealing their voter ID or without revealing to whom they voted. That is zero knowledge proof with secure digital voting. Okay. Anonymous verification. A user can prove certain facts without revealing their exact identity. A prover can prove their facts without revealing the exact identity. Okay. That is about your knowledge proof. What is the knowledge, zero knowledge proof? Alice will prove the Bob that Alice knows the password without sharing the password itself. Okay. The next question in the unit number 2 is, what is identity based public key cryptography? We call it as IBPKC. What is identity based public key cryptography and how does it differs from the traditional public key cryptography? We will have a tabular column and we will be going with a differentiations with point to point. Okay, this question is asked in May 2025 under question number 5. Which question, Nana? This question is, what is identity based public key cryptography? Okay, this IB, identity based cryptography, is a system in which users public key is created directly from their identity rather than random, such as taking the email address, taking the phone number, employee ID or IP address of the employee. That is called as identity based public key. Done instead of traditional public key taking the random number, we will take the personal details of the sender, personal details of the user. So a trusted authority called as private key generator will generate and provide the corresponding private key. Because you might have a doubt, when I share my personal details, what happens? We encrypt it, we keep it in the background and we create what? Index files. Okay. A trusted authority private key generator will generate and provide the corresponding private key for us. Why is this identity based public key is needed? In traditional cryptography, before sending any encrypted message, you must obtain receiver's public key, verify its certificate, then only process your information. Whereas in the identity based public key, it simply transports the data by using the person's identity. instead of verifying the public key, it simply transports the data to the particular user's identity based public key. So your task is simplified and you need not to wait for the certificates. Done dear. That's why we need to use identity based public keys. How does it works? What is the mechanism behind it? First step, setup. A trusted authority will generate the public key generator. No, get that. That is your first step. Second step, right? In the private key, we will have master secret key. We will have system parameters as well. Second step, now you map your public key, the private key what you got from the trusted authorities. No, you have to map that with the public key. Like the user's identity becomes what? Your public key. Example, identity bob@gmail.com, public key is bob@gmail.com. The identity, my personal detail will become the public key. Step number 3, private key generation. Okay, the private key uses master key to generate Bob's private key and securely sends it to him. Now this can be shared with the receiver and receiver can send the message, receiver can receive the message from the Bob. That is your step number 4. Anyone can encrypt a message using Bob's identity, that is bob@gmail.com. Now encrypted data has to be decrypted, no? Bob decrypts the message using the private key received from the PKG. Okay, so first what we have done, we generated the private key, master private key from the trusted authorities. Second step is generating the public key for me. Third step is when I generate the public key, I need to have a private key which I will get from the master key, step 1. Fourth step is I will share this identity to the users. Fifth step is users will send the message, I will encrypt it, I will decrypt it and I will read the message. Okay, this is identity based public keys. And how does it differs from the traditional public key? Because this is the question, no? So public key source derived from user identity only. My personal details like name, mail, phone number will become my public key. Here it is randomly generated. In the traditional, as I said, it is randomly generated. Private key. From the master private key, I will generate a private key. Whereas here, generated and controlled by the user. In the IB, identity base, it is generated by the master private key. Certificates, not required. Traditional, you need to have the authentication. You need to have the certificate from the authorities. Key distribution, encryption possible using the identity alone. Just now as I said, I will share the identity, people can send a message to me, I will decrypt it, I will read it. In the traditional, we need to have a symmetric key and that can be used between the receiver and used between the sender. But here you have your identity alone, you can decrypt the message and you can read it. In the identity based public key, we have escrow risk, that is high as PKG knows private keys. The escrow risk is low as users control private keys. Best use case, centralized environments, open environments like the internet. This is into your organization where you have the centralized environment and you have a trusted networks. This is open network, can be used by anyone. Clear, dear? Now the next question in the unit number 2 is what are potential attacks on simultaneous contract signing protocols and how they can be mitigated, how they can be reduced, what are the problems or potential attacks on simultaneous contract signing timing. Done dear, and I'll share my contract and the receiver will not reply to me in the given time. That can be one of the problem, right? So we will explain, we will see one by one what are the potential attacks on the simultaneous contract signing protocol and how they can be mitigated. Appeared for one time in last year, May 2025, under the question number 5B. Simultaneous contract signing, dear. Simultaneous contract signing is a cryptographic protocol that allows two parties to exchange digitally signed contracts and what are the potential attacks in this process. Okay, so first, what is simultaneous contact signing? You need to understand that is cryptographic protocol where two parties can exchange digital signed contracts. In this process, what are the problems we are going to face? That is potential attacks on simultaneous contract signing. The first one is abort attack. The first attack, potential attack, is abort attack. Then here in the abort attack, what happens is, first one party will receive the other person's commitment or partial signature and they stop participating. One party will receive the other party's proposal or the part of it and they will start replying to it and they will start participating in it. By this, what happens? Alice sends her commitment, Bob receives it, Bob refuses to send his signature. So Bob knows what is the proposal of the Alice. Bob gains information, Alice is left without Bob's signature. Right? This is abort attack, waiting for the other person's proposal and looking into that proposal, knowing everything about it and not replying back to it. That is abort attack. Here the problem is unfair advantage to one party. Bob got the complete details from the Alice. That is biased. That is unfair. Second thing is replay attack. What happens? An attacker records the old messages and reuse them as a new message. That is replay attack. An attacker will use the old messages and they will pretend they will use it as a new message. Example, Alice and Bob complete a signing process, contract signing process. An attacker stores this exchanged messages and then the attacker resends those messages pretending they are new and latest. Right? What is happening here? Alice and Bob complete a contract signing process. Now the attacker will read all these exchanged messages and the same messages will be sent to the user now pretending that they are new. The problem is the receiver may be tricked into accepting old or invalid agreements by sending the old messages. Okay. Next one is, third one is timing attack. What happens is, right, a attacker will exploit the network delays or system timing differences. Attacker will perform what, dear? Network delays or system timing differences. Like Alice sends her signature, Bob intentionally delays his response, Bob gets Alice's signature first, then Bob gains an advantage before sending his own signature. Then this is what, dear? This is timing attack. Timing attack is both people will agree to share the digital signatures at the same time. Alice will send her signature, whereas Bob intentionally delays his response by exploiting the network or the system timing. Then Bob will get the advantage by gaining the signature from the Alice first. Now Bob will send the signature or will stop. Done, dear. One party obtains information earlier than the other. After this, the next kind of problem is how to prevent this. We have mitigation techniques for this. The mitigation technique is, first, bit commitment scheme. In the bit commitment scheme, without revealing the original signature, usually what we do is we will share the information or the encrypted message without sharing the original message. That is bit commitment scheme. Here, each party first commits to their signature without revealing the signature, usually done using cryptographic hash functions. For example, instead of sending the actual signature, we will send a hash signature encrypted. Then Bob will also send the hash signature. Now, based upon the mutual commitment, then Alice will reveal the signature, Bob will also reveal the signature. So, Alice will receive the signature, but it is not in the readable format, encrypted format. Bob will also receive the signature, but it is also not in the encrypted format. Now, when both signatures are transferred, now we will have the chance and we will go with the commitment and we will reveal the signatures for it. And the the benefit from this is no one can change their signature later because message is already sent. Prevents cheating. The second thing is timeout and abort mechanism. Set a maximum waiting time of 5 minutes, 4 minutes. Within the 5 minutes or 4 minutes, I did not receive any message. Done dear. My digital signature will be erased or digital signature will not be sent at all. Done. Like wait for 5 minutes. If one party does not respond within the time limit, the protocol is cancelled. No one gains an unfair advantage. So that you will be able to handle timing attacks, what we have seen in the last section. Done dear. Benefit: prevents endless waiting, reduces abort attacks as well. Abort attack is the first attack what we have seen, no? Gaining the information from the alias, reading the entire information and not responding. That is abort attack. Zero knowledge proofs. A party proves they possess a valid signature without revealing it. That is the zero knowledge proof. No, saying the verifier that I know the password without revealing it. Example: Alice proves that I have a valid signature without actually sending the signature. Benefit: prevents the fraud, ensures honesty before revealing the signatures. Okay, next. Fair scheduling and gradual disclosure. Step by step, we will disclose the signature. Exchange information in small pieces over multiple rounds. Example: round 1 25% signature, round 2 25%, round 3 25%, round 4 25%. So you gradually gain the honesty, you gradually gain the trust on the party, then only you will reveal the full signature. So neither party gets the full signature too early. There is no chance of abort attacks, there is no chance of timing attacks. Prevents timing attacks, maintains fairness. Done. The next question in the unit number 2 is explain in detail about secure multi-party computation with an example. What is secure multi-party computation? Explain it in June-July 2024. We have this question in your question paper. What is multi-party computation? We call it as SMS. It is a cryptographic protocol that enables multiple parties to jointly compute a function on their private data without revealing the data. Right? Without revealing the data, multiple parties can jointly compute a function on the data. That is called a secure multi-party computation. Right? In the beginning of the class itself, I said I have a message and I want to share it with the receiver, but I will be encrypting it. I will be encrypting it. That is this. Without revealing the original data, I can perform the computations with multiple parties again. Purpose of SMC is data privacy. Keeps your data confidential during joint computation. Second thing is correct computation. Produces the accurate results without trusted third parties. Secure collaborations can be established, right? As multiple parties is involved, cooperating among the multiple parties will be trustful, and mistrustful parties cannot get your actual data. Information protection prevents the leakage of sensitive data such as medical, finance, or economical records. Other things are strictly safe. Example: average salary computation. One of the most cited example in the entire internet or the universe about this SMCE is the average salary computation problem, where multiple employees wants to find out their average salary without revealing their individual salary, right? Where many employees of the organizations wants to find out what is the average salary, maybe their designation or the experience people are getting as per their matching to their experience, matching to their designation, what is the average salary they can expect without revealing their individual salaries. They can use this SMC. Let us assume three employees have A, B, C and they want to find out what is the average salary without revealing their original salary. Each employee adds a random number to their salary and passes the total to the next. Anywhere in between, in beginning or in the ending, each and every employee will add a random number. Okay, and it will be sent to the next pass. The final value is returned to the initiator, who removes the added randomness and calculates the average. So for the other parties, the number with random number we added, no, that will be displayed, but the initiator will know that initiator will remove the added number and the initiator will calculate the average. Now the calculated average will be displayed in the group, by which no individual salary is exposed, but the group will get the average result. This method is ensuring the confidentiality and as well as the correctness without revealing the individual data. That is the advantage of using SMC. Applications of SMC. Done here. What is the secure multi-party computation? Collaborative data analytics. We will be able to collaborate with the multiple parties and still we will be able to get the statistics and we will be able to get the average without revealing the actual data. Fraud detection systems detects the fraud patterns while keeping the customer data confidential. Privacy. We will be able to preserve the machine learning. We will be able to train modules on the distributed data without sharing the raw data. Joint auctions and bidding, right? You know the joint auctions, no, people will go for this secret auction. In such cases we will maintain the bid secrecy by adding that extra bit to your actual data. Digital voting and e-governance enables secure private voting without exposing your votes. That ends our unit number 2. Now we will be jumping to our unit number 3, and the first question in the unit number 3 is, what is the importance of symmetric key length? Done. So we will be discussing about symmetric key length in detail. How is it going to impact? How is it going to impact the symmetric key length? Write about symmetric key length in detail, which is appeared in June-July 2024. Symmetric key length is the number of bits in the secret key. As the number of bits are high, the chances of guessing it are low. So it is very important for anyone to have the number of bits in the secret key. That is called as your symmetric key length. Okay, so in the symmetric key length, it is the number of bits in the secret key used for both encryption and decryption. The security of a symmetric crypto system mainly depends upon its key length. As I said, when the key length is high, the chances of guessing the data is low. Okay, example. We have DES, data encryption standard, which uses 56 bits, which is weak and can be cracked with the modern hardware. Trust me, in hours, not in days or weeks. Done with the data encryption standard, which uses 56 bits of data, can be easily cracked. Whereas if you go with the advanced encryption standards, which use a key length of 128 or 192 or 256 bit, are highly secured and which is currently used. The data encryption standards are not currently used, whereas advanced encryption standards are currently used, and it will use 128 bit, 192 bit or 256 bit length key, secret key. Brute force attack. Right, in the very first unit itself, I said the brute force attack. If I have a pin of only 4 digits, the maximum possible chances are how many? 9999. 9999 chances are only there to crack my password. Done. If it is 8 digit or 12 digit, imagine the computation work. Brute force attack cannot easily crack it. Okay, so symmetric crypto systems with shorter keys are vulnerable, can be easily attacked to brute force. Done here. Just now, as I said, if the length is small, chances of attacking is very high. A 56-bit key may be cracked within hours using the hardware. A 64-bit key could be cracked in months or years. Now imagine a 128-bit. Even to the global scales, brute force attempts cannot crack it. Done. A Secret key with this 56-bit can be easily cracked in hours, where a 64-bit key could be cracked in months or years. If you go with 126, 192 or 256, even the global scale brute force attempts cannot crack. What are the threats to short symmetric keys? Just now as I said, if your password is 3 digits, how many chances I have? Only 999 chances. If I try this 999 chances, your key will be simply cracked. Done here. Software crackers. They use brute force programs on multiple computers to break the shard keys within hours. Chinese lottery attacks employs millions of TVs and radios for guessing this, and they will be able to crack the weak keys very easily. Virus based attacks. Virus infected computers which are compromised to the attackers, in the ideal time they will try to clear this, they will try to guess the key. Biological attackers, which is a theoretical method. If it is going to be successful, our entire data is at the stake now, it is at the threat now. A theoretical method which is not successful or currently implemented, using the biological cells for massive parallel key testing. So any key in this world can be easily attacked now when this is going to be successful. Key length importance. Longer symmetric keys greatly increases the security by making the brute force attack impractical. Like we have advanced encryption standards of 128-bit, 192-bit or 256-bit. This is the example which I am saying from the very beginning. If I have a 4-digit pin, it is very easy for me to crack because maximum chances are 9999 only. If I have a 8-digit pin number, the chances of cracking it is damn high. Okay. So what are the threats? Software crackers. Brute force programs run on multiple computers, deployed across multiple networks, 1,000 times slower than the hardware attacks, but it is effective against keys like 40-bit and 56-bit. First one is brute force software attackers. Brute force programs run on multiple computers simultaneously. They have deployed across multiple networks and 1,000 times slower than the hardware attack, but it is going to be very effective against the 40-bit or 56-bit data. Second one, Chinese lottery attack. Like this is just like a lottery system where thousands of people will purchase a lottery, one person will get the prize. Like we will send this to 1,000 people, out of which one people data can be easily extracted. Done. That is called as Chinese lottery technique. Many devices like TV, radios are compromised with the key testing chips, and when plain text is ciphertext pair is broadcast, all devices test keys simultaneously, and at least one TV or two TVs can extract the information and your data is gone. Malware, this a virus infected computer systems at their ideal time will test this keys. Even if each machine tests 1,000 keys per second, a large network can be break. A large network can break weak keys like 56-bit DES within weeks. Low cost but very powerful. The last one is theoretical idea. Living cells perform encryption tests in massive parallel numbers. Concepts like DESOSUR shows billions of cells testing millions of keys per second. Even such methods cannot break long keys like 128-bit. That is why people are advising us to go with advanced encryption standards which has a 128-bit secret key. The number of digits in your password are high, the chances of getting hacked is low. Summary. This threats show distributed parallel and innovative methods can break short symmetric keys. However, the long symmetric keys like 128, 196, 256 remain safe from all the practical attacks. Okay, so this is the importance of the secret key length. As your secret key length is big, the chances of getting hacked is low. Okay, you know XOR, right? Explain the cipher block chaining with an example. Cipher block chaining with an example which is appeared in June July 2024. So now when the encrypted message is sent from the sender to the receiver, what we do is we perform a block chaining such that the last message of your plain text will be added to the cipher text, and the next cipher text will be added to the next plain text. Like this we will maintain a chaining process that is called as block chaining. Here in the cipher block chaining, it is one of the most widely used mode of option in the symmetric encryption. How it enhances the security of ciphers by introducing the chaining between the plain text and cipher text. This method of cipher block chaining is one of the most usually used mode in the encryption technique. And what is the working mechanism of this? It maintains a chaining between the plain text and the cipher text. The working of CBC mode. We need to perform XOR operation. Each plain text block is XOR'd with the previous cipher text block before encryption. Now what is this XOR'd? We call it as XOR gate. XOR gate says that true XOR true is false. False XOR false is also false. True XOR false is true. False XOR true is true. It's just like your magnetism. Unlike poles attract, same poles repel. If we have same bits in the XOR gate, the result is false, 0. When we have different bits in the XOR gate, the result will be true. So we are maintaining a chaining between the cipher text and plain text. The plain text block is XOR'd with the previous cipher text block before the encryption, and this process continues with the entire message. Every plain text block will be chained with the previous cipher text block, and the first plain text block will have a investigating variable. Done here. That variable will go IV. Chaining effect. Encryption depends upon the previous cipher text, producing different cipher text for the identical plain blocks. And this is again going to create one important thing. See, in my plain text, if there is a word which is repeated for 3 times, it is quite easy for the attackers to find out, because these 3 words will have the same kind of cipher text and people can be able to identify it. Now, with this technology of linking the plain text with the previous cipher text, even you have the repetitive word becomes tough to identify. That is this chaining effect. Initialization vector. Just now, as I said, the first block uses an initialization vector instead of previous cipher text block, right? We will use the IV variable for the first block, because first block will not have the previous cipher text, no? So we will go with the initialization vector. From then, the second text block will be linked with the first cipher block. Third will be linked with the second cipher block, and we will go like this. This is called as chaining effect. The formula used in the CBC is as follows. Encryption EK, where the plain text is XOR'd with the cipher text previous block. That is, plain text 1 will be encrypted with the initialization vector. Plain text 2 will be XOR'd with the cipher text 1. Plain text 3 will be XOR'd with the cipher text 2. This is encryption. In the decryption, what we do is the cipher text will be encrypted with the cipher text block -1. Okay. Example. The encryption procedure will be done first. So how do you do this? Let us assume that we have P1, the plain text, and its binary bit is 0001. We have P2 and its binary bit is 1011. IV, the initialization vector is 1010, which is a 4-bit random initialization vector generated for your data. Okay, we have 2 plain text blocks, P1 and P2. P1 is 0001, P2 is 1011, and this is the initialization vector which is randomly selected by your algorithm. Key equals to 1, which is simple additive encryption. That is encryption of x equals to x plus 1. Okay. Step 2. Sorry, step 1. Encrypt the block 1. P1, we need to do the XOR of P1. 0001 XOR with 1010. Done here. What is this 001? This is P1. What is this 1010? This is your IV, initialization vector. You are able to see, no? So I am encrypting the first plain text with the initialization vector. As I said, XOR 01 gives me 1, 00 gives me 0, 01 gives me 1, 10 gives me 1. In the XOR, if both the bits are same, your result is 0. If both the bits are different, your result is 1. So I went with the first bit of P1 with the first bit of IV. 01 gives me 1. Second bit of P1 with the second bit of IV. 0, both of them are same. Hence the resultant bit is false. Third bit is 0, third bit is 1. Resultant bit is 1. Like this we will do. And we have to encrypt. How we are going to encrypt? We are going to add 1 to your resultant bit. The resultant bit is 1011, and for this we are going to do the binary addition manner. In the binary addition, when you perform, we have only two numbers, 0, 1. Right? 0 plus 1 is 1, 1 plus 1 is 1, 0. 0 plus 1 is 1, but 1 plus 1 is 1, 0, because we don't have 2, we have only 2 bits, 0 and 1. That is what happening here. When you add 1011 to 1, I will get 1100 in the binary addition format just now as I explained. Now encrypt this second block, that is P2. Now P2 will be 1011, which is created by us in the beginning, right? And it will be encrypted with 0011, which is the result of the step 1, right? This one will be XORed in the step 2. Again in the XOR, we follow the basic rule. If both bits are same, your output will be 0. If both bits are different, your output will be 1. So you have to add the corresponding bits. First bit 0. Second bit 0, 1, 1. Third bit 1, 0, 1, 1, 1 also is 1. Now again you add binary addition. Now again you perform binary addition. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 gives you what? 1, 0. So 1 will be carry forward and 0 will be added. So we will add 1, 1. You get what? 1, 0. 0 is stored here, 1 is carry forward. Again 1 with 1 gives me 1, 0. 0 is stored, 1 is carry forward. 1 with 1 gives me 1, 0. 0 is stored, 1 is carry forward. 0 plus 1 gives me 1. So when you add 0, 111 to 1, you are going to get 1, 000. This is basic binary addition here. Final cipher text of C1 plus C2 is you just add them. That's it. You just club them, right? 11001000. This is the cipher text which I want to send to my user. Now this will be decrypted. In the decryption process, what you need to do is you need to subtract 1 and you need to perform the XOR. That's you are going to get P1 like this. You are just reversing the order. Okay. And in the block 2, that is C2 equal to 1000, you have to subtract 1, which is added in the encryption. And again the result of C1 should be XORed with the C2. The result of C1 will be XORed with the C2. Done here. Then you will recover the plain text. This is the message of P1, P2, what is encrypted and sent, and we decrypted. Okay. This demonstrates that CBC provides diffusion, meaning a change in one block of plain text or IV initialization vector affects all subsequent blocks of cipher text. This is called as block chaining, cipher block chaining, where every plain text will be blockchained with the previous cipher text, whereas the first plain text will be blockchained with what? With the initialization vector. Okay, let us go with the next question of our unit number 3, that is, what are stream ciphers and how do they differ from the blockchain ciphers? Just we have seen the blockchain ciphers, no? How this blockchain ciphers are differ from the stream ciphers? What are they in the terms of designs, operation and use cases? We need to explain this, which is appeared in May 2025 Osmani University question paper 7B. First, let us understand what is a stream cipher. What is block cipher? The plain text will be chained with the previous cipher text. Now, in the stream, we will encrypt the data bit by bit or byte by byte. Okay, in the stream cipher encryption, we will encrypt the data bit by bit or byte by byte at a time using pseudo random key streams. This key stream is XORed with the plain text to produce the cipher text. Okay, in the chain, what we have done, the plain text is XORed with the previous cipher text block, whereas here we perform the encryption bit by bit or byte by bit, and again this key will be XORed with the cipher text. You have a little more enhanced version of the CBC, that is this. Okay, features: encrypts the data bit by bit, byte by what? Byte instead of the block. In the CBC, we do block by block, block by block. Here, we go still deeper into your data and we encrypt the data bit by bit or byte by byte. Uses a pseudo random key stream and it will be XORed with the cipher text, and it is very extensively used in the voice, video and wireless communication. It has a very low latency and requires very less memory of storage. Types: we have synchronous and we have asynchronous, that is self-synchronizing. In the synchronous, key stream is independent of ciphertext, whereas in the self-synchronous, key streams depends upon the previous ciphertext. Okay, we have two types. The first type is synchronous, where the key stream is independent of the ciphertext, whereas to your CBC, in the self-synchronizing, key stream depends upon the previous ciphertext. Okay, we will see comparative difference between the stream cipher and block cipher. The very first difference is, in stream cipher we will go with bit by bit, byte by byte, whereas in the block cipher we will go with block by block, and block size can be 64, 56, 128. It depends upon the algorithm you are using. Data processing: encrypts data bit by bit or byte by byte. By the name itself, block cipher encrypts the data in the fixed sized blocks. Working: uses a key string and it will be XORed with the plain text. Applies mathematical transformations to each block. Mathematical transformations are going to create a very impactful thing. We have seen in the unit number 2, random number generators. We will also see in the unit number 4. Speed: very fast, which need very less memory to storage. The latency is also high. Slower, but provides what? Strong security. Error effect: errors affects only the few bits, whereas here errors might affect the entire block, because in the CBC last screen, if you just go back for 2 minutes, then here you can see that if one block is miscommunicated, is mismapped, the entire data is also mismapped. That is, errors might affect the entire block, not just one block. Whereas here, if bit goes for one error goes for one bit, it might affect a limited number of bits, because we go bit by bit, byte by byte. Memory requirement: requires very less memory. Here requires more memory for block buffering, because every block is mapped with the previous ciphertext block. Parallel processing: difficult to parallelize because you have to go step by step, bit by bit, byte by byte, but supports parallel processing in some nodes. Done here. Applications used in wireless voice video communications, used in file encryption and secured storage. Right, one simple tip for quick revision is stream cipher. fast real-time data. Block cipher, slower but more secured. Strong stored data. Right, next question in the unit number 3. Compare between public key versus symmetric encryption. The first question what we see is symmetric encryption, where a private key is shared between the sender and receiver. Sender encrypts the data with the private key. Same private key is available with the receiver. Receiver will decrypt the data and receiver will read. Now we are going with the open key, that is the public key. And how is it different? How is it different from symmetric encryption? Okay, public key cryptography, symmetric key cryptography. In the symmetric key cryptography, it uses a single shared secret key between two users, but for both for encryption and decryption. You know this. First is public key cryptography. It uses pair of keys with the public key used for encryption, and we will have the separate key for decryption, right? And the private key used for decryption. Okay, in the symmetric we have only one secret key which is used between sender and receiver, whereas in the public key cryptography we have a public key for encryption and we have a private key used for decryption. Okay, this is a major difference. We use two keys in the public key, we use only one single secret key in the symmetric. Second one, it does not require a secure channel because it is public and it is open for everyone. In the symmetric, it has to be secretly shared with the user, because if someone steals, the entire message is also gone. That's why we need to have a secure distribution of the secret key between the communicating parties. Public key, it performs encryption more slowly and is computational intensive. It is very fast and well suited for encrypting large volumes of data because it is node to node, party to party, whereas this one public. Hence, it is going to be very slow and it is computationally intensive. Public key requires longer key sizes such as 2048 bit RSA in achieving strong security. Imagine how big a number is this, 2048 bit RSA. Whereas this one achieves this strong security which 128 bit AES. The symmetric key achieves the security between the users with the shortest keys of 128 bit. Whereas if you want to acquire the security in the public key, it has to be a 2048 bit length key. Public key provides authentication, integrity, and non-repudiation. In addition to confidentiality, we also have this integrity, authentication, and non-repudiation. It mainly ensures confidentiality and needs additional mechanisms for authentication, because anyone holding the symmetric secret key can access your data. So there is no authentication for it. Whereas here it is kept in the public, only the user with the private key can access the data. Hence it is public, everyone can access it. No, it is public, but only the user who is authenticated with the private key can access the data. So it ensures confidentiality, where here I need to adapt different mechanisms to ensure that. The sixth difference is public key scales efficiency. Why? Because each user needs only one key pair regardless of the number of correspondence. You may have any number of users, right? There is one public key where everyone can access it, but one individual user will have only one private key corresponding to that fellow and they can decrypt the data. Whereas here it does not scale because n into n minus 1 by 2 unique keys are required for n users. Suppose if there are 10 users, I need 45 unique keys for 10 users, right? If there are 10 users, I need how many unique keys? 45 unique keys are required. Whereas here one public key and one corresponding private key to the individual user. It is best suited for exchange of digital signatures and identity verification, whereas symmetric is best suitable for communication of bulk data between two or more users. Done here. These are the differences between the public key encryption and private key encryption, symmetric encryption. We will jump to our unit number 4. In the unit number 4, the very first question is, what is number theory? Explain in detail. What is number theory? Explain in detail with an example. In June, July 2024, we have this question. See, the number theory is one of the important mathematic branch that it deals with the integers and their properties. Okay, number theory is one of the important branch of mathematical computations that deals with the numbers and their properties. It forms the mathematical foundation for the modern cryptography, and it is widely used in the encrypting algorithms such as RSA. Right? Even in the previous units also we have seen the importance of random number generators. Done here. This mathematical foundation for the modern cryptography. So number theory is going to be the most important aspect. What are the components? The components is modular arithmetic, performs the calculations using a fixed modules. First thing is, we will go in deeper with the what is modular arithmetic in the next coming screen. It performs calculations using fixed modules. Second thing is prime numbers, fundamental numbers used for securing your key generation. We will discuss all those things, right? Prime number factorization is going to be the most important technique in the mathematical cryptography. Okay, greatest common divisor determines the two numbers greatest common divisor. Now it gives the biggest multiple of these two numbers, that is greatest common divisor. Modular inverses, numbers used to reverse operations in modular arithmetic. The operations what we performed in the modular arithmetic, no, we will reverse it, right? We will try to find out the modulus of a number, and we will also find the inverse modulus of a number, that is modular inverse. Euler's totient function counts integers relatively prime to a given number, right? Counts the integers relatively prime to a given number. So if n number is given, I will try to find out what is the n minus 1 prime numbers, right? If n is given, we will try to find out what are the n minus 1 prime numbers. Feynman's little theorem helps in modular exploitation and inverse calculations. And we have CRT, which solves concurrence and speed up the cryptography computation. Right here, these are the important components of number theory in the cryptography. Confusion and diffusion is one of the important technique that hides the key relationships and spreads the plain text patterns. Unicity, distance, and entropy measures the exact uniquely determined plain text and accesses the security strength. Right? What is unicity, distance, and entropy? It measures the cipher text needed to uniquely determine the plain text and access the security strength. Let us go with the example and let us try to understand prime number factorization, totient equation, modular inverse. Done here. What all these things we will see with an example. Let us have an example of a modular arithmetic. Suppose there are two numbers 10, 13. Right? We will try to find out what is the modular inverse of this number. 10 plus 13 modulus 22. So when you do 10 plus 13, you get 23. When you perform the modulus of 23 by 12, you are going to get the remainder. You know, modulus gives the remainder, division gives you what, Nana? Quotient. So when I add 10 plus 23, that is, sorry, 10 plus 13, that is 23. 23 modulus 2, right? I am going to get 11. 23 modulus 12, I am going to get the result as what? 11, because 23 is not exactly divisible by 12. 12 into 1 is 12. 23 minus 12 is how much? 11. This shows how the number wrap around with a fixed range and a concept widely used in encryption. This modulus concept is one of the important wrap around concept which has a fixed range, and it is very much extensively used in the encryption. Okay, so we will see the detailed way in this particular diagram. What are the side headings we have seen? With examples we will try to understand now. Little more focus please. First one is modern. We call it as modular arithmetic. Here we will calculate with respect to the fixed module. Suppose if two numbers are given, I will try to find out what is the modulus of it. 10 plus 13, modulus of 12 will be 11. Just now we have seen the example. Next thing is prime numbers. Integers greater than 1 that are divisible by itself and 1 is called as a prime number. You know this definition. Integers that are greater than 1 that are divisible only by 1 and themselves is called as a prime number. Used for generating secure keys in the cryptography. Prime numbers are used for generating the secure keys in the cryptography. Trust me, we will be generating a prime number of 2048 bits. 2048 bit length prime number will be generated for this secret key. Such a big number will be generated so that strong numbers will create strong keys. Strong keys are not easily hacked. That is what the concept of prime numbers here. Greatest common divisor. When you take two numbers like 15 and 28. See, 15 is divisible by 1, 3, 5. 28 is divisible by 2, 7 as well as by 4. Now in this two multiples for 5, 15 I have 1, 3, 5. Whereas in the 28 I have 2, 4, 7. Out of this 3, which one is common? 1 is common. That is greatest common divisor. The greatest common divisor finds the largest number that defines two numbers completely. Done. Out of this there is only 1. Modular inverse. For a mod of n, suppose there is a number a and you are doing the modulus by n. X is the modular inverse. If a modulus n is performed, then x will be the modular inverse such that a into x mod of n will be equal to 1. Done here so that encryption and decryption will be taken place. This is modular inverse. Euler-Student function. Right, in the Euler-Student function, we will count the number of integers less than n that are relatively prime to n. Right, if n is a prime number, we will count the number of integers that are less than n relatively prime to n. That is, for prime number p, totient of p equals to p minus 1. Next, Fermat's little theorem. If p is prime and a is not divisible by p, suppose p is a prime number and a is a number which is not divisible by p, then a raised to the power of p minus 1 is equivalent to 1. That is modulus of p. Use it to compute modular inverse. Again, encryption and decryption techniques can be done by this modular and modular inverse. Chinese remainder theorem, we call it as CRT, solves the systems of congruence and pairwise relatively prime moduli. Used to speed up modular computations in the cryptography. The CRT is exclusively used to speed up this Fermat's little theorem or Euler-Student function. Confusion and diffusion is a Shannon principle. Confusion is what? Substitution. It hides the relationship between the ciphertext and key. Confusion, it will create the confusion to the attacker by hiding the relationship between the ciphertext and key. Diffusion is what? Spreads plain text redundancy across ciphertext. Spreads plain text redundancy across ciphertext. The last one is unicity distance and entropy. Unicity distance is minimum ciphertext length required for uniquely determining the plain text. It is the minimum ciphertext distance required to predict the plain text. Entropy measures the randomness or the uncertainty in evaluating the cryptography strength. Okay. We will go with the second question of unit number 4. what is the history and background of the data encryption standard DES, and why it was used as the initial federal standard of encryption in the United States during 1970s. Okay, what is DES? Data encryption standard, and why it was initially used as a federal standard for encryption in the United States during 1970s. This particular question is asked in May 2025 under question number Q8. Understand, the data encryption standard was the first widely used symmetric encryption algorithm by the US government in 1970. Done here, the DES was the first national wide used symmetric key encryption algorithm in the US government. So we will go with the history of DES. The first, in 1973, the National Bureau Standards (NBS), which is now called as National Institutes of Standards and Technology, invited proposals for the national encryption standard. Okay, in 1973, the NBS, National Bureau Standards, which is currently called as National Institute of Standards and Technology, invited proposals for a national encryption standard. Now, IBM submitted an algorithm which is called as Lucifer. Right, when the National Bureau Standard has asked proposals for the encryption, IBM has submitted an algorithm called as Lucifer. Then National Security Agency NSA reviewed and modified the Lucifer to improve security. Okay, IBM has provided a security encryption algorithm called as Lucifer. Now the National Security Agency has reviewed it and modified the Lucifer for improving its security. In 1975, this algorithm was published as a draft, that is FIPS, Federal Individual Public Sector, done here, publication 46. The algorithm was published as a draft standard, we call it as FIPS publication 46. DES faced two important criticisms. One criticism is it has only a security key of 56 bit length. 56-bit key was considered to be too short. Secret S-box design raised the concerns about the possible NSA trapdoor. Now, the DES follows a bit key length of 56 that can be easily hacked. And the second important thing is S-box. In the S-box, we will be able to store the data. Then the DES came with the advanced features like AES, advanced encryption strategies, which comes with the 128-bit, and the S-box challenge were also handled. The S-boxes were designed to resist differential cryptanalysis, by which the DES has again uploaded into AES and started widely using. In 1977, the data encryption standard was officially adopted by FIPS publication 46, becoming the first federal encryption standard. Okay, in 1977, DES, after solving this 56-bit challenge and S-box's challenge, officially adopted as FIPS publication 46, becoming the first federal encryption standard. It reminded the standards, and again it came with the different versions in 1983, 88, and as well as in the 1993. Due to growing security threats, DES was eventually replaced by the triple DES and as well as AES. In the triple DES, what we do is we encrypt, decrypt, and encrypt. In the triple DES, what we do? We encrypt, decrypt, and again we encrypt. And we also started using advanced encryption standards AES. Instead of 56-bit, we replaced it with the 128-bit, 196-bit, or 256-bit. Why was DES chosen? Right, by the federal government of US. Provided a standardized encryption method based on IBM. It is well tested Lucifer algorithm. It is based on that. Offered strong security for the technology which is available way back in 1973, and efficient and practical for implementation and hardware. These are the reasons why it was being chosen by the US government. because it is based on the IBM tested algorithm Lucifer, and it was quite able to handle the technology which was available in 1973, and more important, it was practically possible for the implementation. We'll go for a quick revision. In 1973, US government has sent the proposals for the encryption algorithms, and DES was one among it. The National Bureau Standard requested encryption standards, and IBM Lucifer was submitted, which was modified by the National Security Agency. In 1975, a draft was released called as FIPS Publication 46. Main issues what? 56-bit key and secret S boxes. And it was replaced by the triple DES. Triple DES will go a technique called as encryption, decryption, and again encryption. And we also handled the S boxes with the typical cryptanalysis, and we also implemented AES, Advanced Encryption Systems Standards. One line summary. DES was the first US federal encryption standard which was chosen in 1970 for its strong and practical security. But later it was replaced by AES and triple DES because of two simple challenges: 56-bit length key and S boxes, secret S boxes. Okay. Discuss in detail about different database variants, which was asked in June July 2024. What are the different DES variants? Data encryption standards, like this has faced a very big problem because of 56-bit key, which is easily hacked by the brute force attacks. So we went with the several versions of the DES, which is commonly known as DES variants. Okay, so the data encryption standard has faced a serious backlash because of its 56-bit. Now we went with the different kinds of variants of this DES. On a whole, it is called as DES variants. They aim to retain the original DES structure while increasing the cryptography strength. Right? They aimed for the same, retaining the same structure of DES while increasing the cryptography strength. Among these variants, the first variant is triple DES. As I said previously, in the triple DES, we do 3 times with multi keys, that is encrypt, decrypt, encrypt. This variant applies DES 3 times with multiple keys, increasing security to 112 or 168 bits. So, we have a plain text, we will encrypt it. The encrypted data will be decrypted. And again, I will use one more key for decryption. Now, I will use one more key for the decryption data to encryption. Now, this will be converted into ciphertext. By this, you are going to have a higher security to your data. Now, this can be decrypted as well. The ciphertext with one key, the same key what I used there, I will decrypt. Again, I'll use the same key what I used in the previous encryption for this. Then the same key will be used for decryption. Then you are going to get the plain text. This is called as triple DES. Encrypt, decrypt, encrypt. When it comes to the decryption, decrypt, encrypt, and as well as decrypt, so that your ciphertext will be converted into plain text. The second variant was DES with the independent subkeys. So here what we have done is we used 16 independent 48-bit round keys, right? So 16 into 48 gives me how many bits totally? 768 bits. So if your data has been placed for 48-bit round keys, we are using 16 independent 48 round bit keys, so that overall bits increased to how many dear? 768, by which the stronger keys were developed and where we were providing the strongest security for your data, providing stronger brute force protection but still vulnerable to different attacks. Third one, DESX. Here we add a 64-bit whitening key before and after the DES encryption. For your data, a 64-bit whitening key was padded before and after the encryption, increasing the total key size to 120 bits and enhancing the security. Because the number of bits increases, the chances of brute force is low. So what we have done, we have added 64 whitening bit before and after the encryption. Crypt 3, a Unix password encryption variant that uses key dependent DES permutations, making the hardware based attacks very difficult. It is Unix password technology encryption variant which uses key dependent permutations by which your data is going to be more secure. Generalized DES, we call it as GDES, it divides your data into multiple subblocks. It divides your data into multiple subblocks and added more rounds to improve the security. Though fewer rounds make it vulnerable. Again, if you add more rounds, it is very safe, but we go with the fewer rounds, it has a problem. Done. What we do is we modify the DES with multiple subblocks. We divide the block into subblock and we shuffle them. We rotate them with more rounds. Then here we apply the encryption at different levels, like we have seen in the last point. We went with this 16-bit data for 48 rounds. Okay. DES with alternate S box and key dependent S box. Here we modified or we dynamically generated the S boxes. We modified or we dynamically generated the S boxes to increase resistance against the various or differential linear cryptographies. RDS, which is called as rotated DES, it replaces the traditional swap operation with the key independent operation. Right? Instead of going for the multiple rounds with the traditional swapping process, we replaced it with the key dependent swap. By this, you had an improved version of your DES. This variance collectively aim to increase the key length. As I said, the main goal is increase the key length, because the number of key length is increased. Then here what happens is you have a better security. So you introduce irregularities, you go with enhanced resistance, and different methodologies can be performed for your compatibility. Okay, a very quick revision. 3 DES applied 3 times. Independent subkeys, different keys are used for each round. DESX added whitening 64-bit keys. Crypt 3, Unix password encryption. GDES, more rounds and sublocks. Alternate S boxes, modified or dynamically generated S boxes. RDES, key dependent swapping instead of traditional swapping. Okay. The last question of your unit number 4, what is linear congrutional generator and how it is used in the cryptographic systems? The linear congrutional generator, which is called as LCG, is a deterministic algorithm that generates a sequence of pseudo random numbers using the formula xn plus 1 equals to a of xn plus c modeled by m. Okay, what is this LCG? It is a deterministic algorithm that generates a sequence of pseudo random numbers using this formula, where a is called as multiplier, c is called as increment, m is obviously modulus, and x naught is the seed, we call it as initial value. Done here, x of n plus 1 equals to a of xn plus c modulus m, where a is called as multiplier, c is called as increment, m is modulus, x naught is the initial value. What are you doing here? You are generating a deterministic algorithm that generates a sequence of pseudo random numbers. This pseudo random numbers, which we generated dynamically, will be padded with your message so that your message will be encrypted. That is LCG. This formula generates a sequence of values like x1, x2, x3, so on, that appear random but are completely predictable if parameters and seed is known. The initial value is known and which parameter you are following, it is easy to find out. So how does it work? Begin with the initial value x naught, apply the recurrence relation to generate the next value, repeat the process for generating the pseudo random numbers as your number of blocks. The important applications is key stream generation can be done, session key deviations can be done, initialization vector generation which we used in the different algorithms, done on assimilation and testing. Okay, so see, in the unit number 2 we went with the importance of the numbers, and in the unit number 3 we went with the random number generations, done, and these things are padded with your original message to provide a stronger security, done. Now, how is this chosen? How are you going to choose the initialization variable for your ciphertext blockchain by using this LCG? Okay. Limitations. Predictability. If you know the pattern and the seed, it is easy to predict the entire sequence. This is the disadvantage. Not cryptographically secure. Done here, it is very linear structure, so it makes the data exploitation very easily. Short period for poor parameters. Poor parameters choices can produce short and predictable sequences. Numbers is weak, keys are also weak. Susceptible to state recovery attacks. A few outputs can reveal the internal state and future values very easily. Done here, these are the limitations. If you see the limitations clearly, the first limitation, known parameters and seed allow to predict the entire sequence easily. If you see the last one, a few outputs can easily reveal the internal state, the seed value as well as future values. Okay. Explain about stream cipher using LFRS in detail. LFSR based stream cipher, what is this? An LFSR is a shift register, left shift register that generates pseudo random bits using the XOR feedback, and it's commonly used for cipher key stream generations. Okay, so working of this LFSR, well, first shift register consists of n flip-flops, done here, where bits shift on each clock pulse. On each clock pulse, the bit will shift to the left side. That is called as LSFR. Maybe if you know the bit operators, bitwise operators, you know the left shift operator, right shift operator. No, this is very much similar to that. Feedback function determines which bits are taped. We will get a feedback immediately. Which bits are taped and XOR'd to produce the input for the next shift. Based upon the feedback what we receive, we will generate the key stream for the next bit. That is called as feedback left shift generator. Okay, types of LFSR based upon the generators, we have the Jiffy generator, which is the basic combination, uses the LFSRs generating this separate output bit by using this formula. The Jiffy generator Z equals to x1 raised to the power of x2 XOR'd with the negation of x1, and that is raised to the power of x3. Done here, so that here we will be generating the combinations of 3 LFRs. Okay. The second one is threshold generator. We call it as majority logic generator. In a threshold generator, multiple LFSRs are used, often 5 or more than that, and the output is the majority of the selected bits at each clock cycle. At each clock cycle, we will move the bit to the left hand side, and we will at least perform 5 or more cyclic process, and in this cyclic process, the bit which is selected for the majority of times, that will be identified. That is threshold generator or majority logic generator. Third one, Goldman cascade generator. It was proposed by the Dieter Goldman, that's why it is called as that. This generator forms a cascade of LFSRs, where the output of each LFSR round controls the clocking or connect to the next. In previous one, what we have seen, for every round the majority is selected. This, after every round, we will control the clocking or content of the next round. That is called as Goldman selection. The cascade structure creates the interdependencies and non-linearity. Done here. So we will have the XOR gate from the round 1 of LSR, and this one will control the second LSR, and the result of this one will control the next, and it will go on for the K. Done here. So on for the available blocks will go, right? Working principle. The LSR round 1 controls the clocking of LSR round 2. The LSR round 2 will control the clocks of LSR round 3, and it will go on. Final output is derived from the last LSR. Okay. Fourth one is multi-sped inner product generator. It is an advanced architecture which uses multiple LFSRs clocked at different speeds. An inner product operation which applies the bitwise AND followed by XOR as the combination function. Again, as I said, if you are aware of the bitwise operators, we have to perform both bitwise and as well as XOR as a combined function to generate your next stage of LSR. Okay. We will jump into our unit number 5, the last unit of our syllabus. In this, we will be discussing about what is secure hash algorithm, which is called as the SHA family. Done here. Discuss in detail secure hash algorithm SHA, which is appeared in June-July 2024. What is the secure hash algorithm? It is a cryptographic function which is designed by the NSI, the National Institutes of Standards and Technology, which is previously called as NBS, National Bureau Standards, to provide the data integrity through the secure messaging digest algorithm. Okay, what is this SHA? This is the hashing algorithm which is proposed by the National Institute of Standards and Technology. It is a cryptographic function which increases the data integrity through secure message digest generation. It is a part of the SHA family, which includes SHA1, SHA2, SHA3, 256, 384 and 512. Types of SHA. We have SHA1, which produces 160-bit output. It is no longer recommended due to its vulnerabilities, because 160-bit output may be the weak and it generates the weak keys. SHA 256, 384 or 512 are the latest technologies which offer increased security and widely used in the most of the cryptographic systems. The working principle of SHA is, the first thing is message padding. In the message padding, what we do is we pad the input so if the length becomes to multiples of 512 bits. Whatever the length of your data may be, we have to add the bits so that the length becomes the multiples of 512 bits. Then block division. This 512 bits will be, this big message will be split into 512 bit blocks. What is the first one? Whatever your message may be, you have to add the bits such that it will become the multiples of 512. Second is divide this padded message into 512 bit blocks. Hash initialization. Initializing the fixed hashed registers with predefined constants. Then we go with the rotations, XORs and modular additions so that your data will be secured or encrypted. Okay, we have to pad the message such that it will become multiple of 512, split the message into 512 blocks, then initialized hash registers on these blocks, and finally what? Perform rotations, XORs and modular additions. Finally, what are we supposed to do? We have to go with the hash generation. See, in the hashing, what happens is on the original data, we apply a hash table. So if any user wants to access the original data, this is safe, this is not visible. People go to the hash table will have a pointer to the original table. I'll show you with the help of a diagram here. First, message padding. If ABC is my original message, I have to add the bits such that it will become the multiples of 512 bits. We have to add so many bits so that it will become the multiples of 512 bits. Next, block division. This final message should be divided into blocks of each 512 bits. Third step, on these blocks we have to assign the hash keys like h0, h1, h2, h3. As I said, user will contact this hash table. This hash table will have a pointer to the each block, so that message is safe, hidden, and user can access with the hash table. That is message scheduling and bounds. Now this 512 block, what we have now, we will compress the functions, we will apply the bitwise rotations, we will apply modular additions, we will apply XOR operations, and we will shuffle these blocks. Finally, hash generation. Block 1 will be processed and it will be joined to the hash. Block 2 will be processed and it will be joined to the hash. So if user wants to access the block 1, user will go with the hash message A3. User wants to access the block 2, user will go with the message as F5. By this, your original data is safe and user is visible to your encrypted messages. What are the applications of SHA? The applications of SHA is, it is very widely used in the verification, it is very widely used in the authentication and identification of digital signatures. Second one, integrity verification. It detects any changes made to your file. Any data change made to your file, it is easily detected. Then it goes with the blockchaining also. It links the blockchain transactions. Password hashing. The passwords will be securely stored in the hashed format. And it is the final one is, it provides the authenticity of software updates before installation. Right? It provides the software authenticity. Passwords are kept safe. Blockchaining can be achieved very easily, integrity can be maintained, and it will verify and authenticate the digital signatures. So, as I said, we will be authenticating the digital signatures. Now we will understand what is the digital signature algorithm. Right? This is the second question in your unit number 5. What Write and explain the digital signature algorithm, which is appeared for 2 times, whereas in Q2 and as well as in the question number 10, done here in 2024. A digital signature ensures that authenticity and integrity of the message by generating and verifying the digital signatures. It does not provide encryption, it only provides what? Digital authenticity and verification. Remember that. Digital signature algorithms are used to ensure the authenticity and verification, but not encryption. The digital signature algorithm parameters are, we have a prime number P. A large prime 512 or 1024 bits, where we will take a large prime number which is equivalent to 512, 1024 or 2084 bit number. You will be taking such a big number which will be equivalent to 512 or 1024 bits, that is P. Prime number Q. Then here we have a 166 prime factor of P minus 1. The prime number whichever you have chosen here, we need to choose the prime factor here, that is Q. Then we have G. It is a generated computer by using P, Q and H. Hash functions uses a cryptographic hash functions such as SHA to create a message digest. Just now we have seen the SHA, no? We create what? Hash messages on your original data. Private key X, a secret random number which satisfies the rule that X will be greater than 0 and less than the prime factor Q. Per message secret number key, again it is a unique number per each message which satisfies the condition greater than 0 and less than Q again. Public key, which is computed as y equals to g raised to the power of x. Give me 2 minutes please, I'll be back. Sorry for the interruption. So we were discussing about digital signature algorithm, which ensures the authenticity and verification, but not encryption. So what are the parameters? We have a large prime number p, we have a prime factor q, and we have the g, which is a generator from p, q, and h. Then we go with the hashing functions like sha. Then we have a private key x, which satisfies the rule it should be greater than 0 and less than q. And we also have per message secret number k, which also should satisfy greater than 0 and less than q. Then we go with the public q. Then we go with the public q, which is computed as y equals to g of x, which is modulus of p. Signature generation process. I will show you the simple signature generation process for the letter M. The following steps are carried out. So first, generate a random number k such that it is from 0 to q. Compute the signature component R equals to g of k modulus p. Model q. Compute the signature component S equals to k of minus 1. Here h of m is the message digest of m using the SHA1. K of minus 1 is the modular inverse of k and q. The final signature of the pair is R of S. Okay, we will continue with the next question. 2 minutes break again, please. So after digital signature algorithm, we will go with the next question of our unit number 5, which is Diffie-Hellman key exchange algorithm, which is appeared in May 2025. And the question says how two parties are securely exchanging the cryptographic keys over an insecure communication channel. So what is this Diffie-Hellman exchange algorithm? Is here the public key cryptographic protocol that allows two parties to securely exchange a shared secret key over an insecure channel, right? And how are we going to do this is, first, a large prime number p and a primitive root alpha modulo p are publicly agreed upon. First, we have to choose a prime number, large prime number p, and a primitive root alpha, such that modulo p are publicly agreed upon. Then, private and public keys. User A selects a private key and computes public by key x, that equals to alpha to the power of a modulus p. Same way, the user B also selects a primitive key b and computes public key as y equals to alpha raised to the power of b modulus p. Now, these keys are exchanged between the user A and user B. I will be showing with an example such this. I have chosen a large prime number p equal to 23 and alpha value is equals to how much? How much? 5. This is the primitive root. Let us assume that p is the prime number which is chosen, that is 23, and alpha value is how much? 5. Now A chooses a random number equals to 6. B chooses a random key that is equals to 15. Now when A chooses a random number equals to A, as per our formula, we have to complete x equals to 5 raised to the power of 6 modulus of 23. That equals to how much? 8. Done. Then B chooses the private key that is 15. So we have to complete as per our formula y equals to the alpha what we have 5 raised to the power of private key B modulus 23, that is the prime number P. You are going to get the value as 2. Now A receives 2 from the B, computes key equal to 2 raised to the power of modulus 23, again that is 18. Now B receives the value from the A, that is how much? 8. B receives 8. Perform the computation. K equals to 8 raised to the power of 15 modulus 23. That gives you the value as 8. Now both the parties A and B will share the same secret key 18. Like this, two parties will share the secret key over the unsecured networks. How? A will randomly choose a number and then we'll perform the computation. B will choose a random number and we will perform the computation and we will share them across on a non-secured public. And where we use them in the session layers. If you know the ISO architecture, we use them in the session layers of hypertext transfer protocol, where we establish the session keys for secure web communication. As well, we use them in the VPNs, where we will exchange the encrypted communication tunnels. Last one, secure messaging systems generates the security keys for end-to-end encryption. Okay. Explain about ISDN with an example. What is ISDN? ISDN stands for Integrated Service Digital Network. When a user wants to establish a secured digital network, we have to go with the ISDN, that is Integrated Digital Service Digital Network. In the ISDN, what we do is we establish a standard communication system. We establish a standard communication system that enables the simultaneous transactions of voice, video, images, data over the existing telephonic lines. Okay. In ISDN, what we do, we establish a communication system such that we simultaneously transport the data like voice, video over the telephonic lines. It replaces traditional analog systems with the faster and more secured digital connections. With the help of a diagram, I'll be able to show it very clearly. So where we use the integrated applications, like it supports voice, video, fax and data communication on a single line. The example for secure ISDN call between user A and user B is: first, user A sends a request to communicate with the user B. Call request will be sent to the user B across the ISDN network. Now ISDN network will follow a challenge and response algorithm. The ISDS system uses what? A challenge and response protocol to authenticate both users. Now both users will receive the challenge and response, then the user authentication is successful. When the user authentication is successful, a common secure session key will be generated and any communication will be established with the help of this common session key only. Once this is established, now the encrypted voice, data, video messages will be sent over this session key across the user A and user B. And as well, the ISDN will also continuously monitor the secure through switching the centers, right? ISDN will also continuously ensure that the session is securely managed through the switching centers. The ISDN switching centers are available, by which we will ensure there is no interruption in the communication. This is the ISDN call between user A and user B. Okay. We'll go with the last question of our session and unit number 5. Discuss in detail about International Standard Organization's authentication framework, that is ISO authentication framework. June, July 2024, question number 11B, we have this question. What is authentication framework X.509? It is a certificate based authentication framework. What is ISO authentication framework? It is a certificate based authentication framework that provides a trusted identity verification in open networks and forms the foundation of public key infrastructure, we shortly call it as PKIs. Right? What is this ISO authentication framework? It is a certification based authentication framework that identifies the trusted verification in the open networks. Main purpose, identity verification, right? Certificate based identity verification, that is what we have seen in the introduction. It authenticates users and as well as devices in the distributed systems, so that we will have a secured communication. How come I am going to identify, or how come I am going to give the verification to the trusted devices and users based upon the digital certificates? These digital certificates are issued by the trusted certificate authorities. We call them as CAs for authentication. And the structure of this X.509 certification consists of version number, serial number, issuer name, that is the CA identity, validity, subject name, subject public key, and signature of the CA certificate authenticator. Then we have the version number, serial number, algorithm identifier, issuer name, validity period, subject name, subject public key information, and as well as signature of the CA. So all these things are available, and out of which issuer unique name, subject unique name identifier, and extensions are what here optional. Now this information will be given to the hashing algorithm, and then it will be supplied to the digest algorithms. Signature algorithms comes into the picture, and then we will get the hash algorithm ciphertext for parameters. So that this is the format of X509 authentication service certificate. Now this certificate will provide the trust and verification on the devices, on the connections. Okay. So certificate hierarchy and trust path. Trust is established to a certification path, linking end entities via intermediate certificate authorities, and that will be routed to a higher CA. Okay. Trust is established through a certification path. We will be linking this intermediate CAs to a main CA, that is the root CA. This hierarchical structure enables cross-domain trust even if the user and verifier belongs to different administrative zones, right? This hierarchical structure will ensure the authentication even the users are from the different administrative zones. Authentication protocols, that is X509, supports the following three types of authentication modes. The first one is one-way authentication. The sender sends a signed message and certificate to the receiver directly one-on-one, that is one-way authentication. Sender sends the message and as well as the signed certificate for the trust. Two-way authentication. Both parties exchange the certificates and digitally signed messages. And the last one is three-way authentication. Avoids the use of timestamp and involves three messages to establish mutual authentication securely. Right? These are three modes for establishing the trust. What are the applications of ISO authentication framework? The application is the hypertext transfer protocol, which provides the secure and authentication web communication where a client can send a request to the server and server will respond back. VPN system will be able to establish secured encrypted network tunnels so that you will be able to access the data which is in the different administrative zone. Email security supports sender authentication and message integrity in the protocols like MIME. Software signing, before the installation, we will be having the verification of the authenticity and the integrity of software application so that you can trust and you can install the software. Last one is enterprise login systems, authenticates the users and controls secure to organizational resources. Okay, this ends here the session for the day. For the important questions, for the notes, PDF and this PPT, Please subscribe to our channel and download the SIA application. All the very best for your end semester examinations. Thank you. I'm Shrikant signing off for the day. Thank you all.